Asteroids, ancient remnants from the birth of our solar system, silently drifting through the cosmic void. They were essential in our planet's creation, but they also carry the power to end life as we know it. In the face of this existential threat, humanity has turned to science, launching two daring missions, NASA's DART and ESA's Hera, to confront these celestial giants and provide us with the knowledge necessary to one day potentially save us from a true cosmic cataclysm. First, let's start with NASA's DART mission. DART, which stands for Double Asteroid Redirection Test, was the world's first mission aimed at testing a method to alter the orbit of an asteroid by deliberately crashing into it. And yes, you heard that right. NASA purposefully crashed a spacecraft into an asteroid, and it was a huge success. Launched in November 2021, DART targeted the binary asteroid system Didymos, specifically aiming for the smaller moonlet named Dimorphos, which orbits the larger Didymos. The goal? To change the trajectory of Dimorphos by slamming into it at high speed. DART slammed into the moonlet at 6.6 kilometers per second, fast enough to cover the distance from New York to London in about 10 minutes. But why did NASA specifically target a unique binary asteroid pair? Firstly, most singular asteroids have long orbits around the Sun, meaning that any change caused to their orbit due to DART's impact would not be apparent until long after, potentially even years after the collision. With the Didymos binary system, the moonlet orbits the parent asteroid in under 12 hours, meaning that scientists would be able to observe any slight change in the orbital period of the moonlet in a much quicker time frame. Secondly, the orbital plane of Dimorphos is aligned in such a way that from our view, the moonlet goes behind its parent asteroid, becoming completely obscured for a period of time in its orbit. This alignment allows scientists to use a measurement technique known as the transit method in order to precisely observe the change in the moonlet's orbital period by noting the change in luminosity of the parent asteroid over time. On September 26, 2022, DART successfully impacted Dimorphos, and after weeks of analysis, NASA confirmed that the spacecraft's collision shortened Dimorphos' orbit around Didymos by 33 minutes. NASA had defined a minimum successful orbit period change of Dimorphos as a change of 73 seconds or more, meaning that the mission surpassed their set benchmark by over 25 times, thus proving that kinetic impact could be a viable method of deflecting asteroids that might be on a collision course with Earth. So, let's dive a bit deeper into how kinetic impact works. In space, due to the absence of friction or atmospheric drag, objects in motion stay in motion, unless acted upon by an outside force. By crashing a spacecraft into an asteroid at a very high velocity, DART transferred its energy and momentum to Dimorphos. Imagine a game of pool. When the cue ball strikes another ball, it transfers its momentum, changing the direction and speed of the second ball. Kinetic impact works in a similar way. The DART spacecraft weighed about 570 kilograms, and it hit Dimorphos at around 6.6 kilometers per second. This transfer of energy was enough to slow Dimorphos just slightly, altering its orbit around Didymos by about 33 minutes. While that may not sound like much, in the context of orbital mechanics, it's a significant shift. We can see just how much energy DART impacted Dimorphos with by using the formula for kinetic energy. At the time of impact, the spacecraft weighed approximately 570 kilograms and was traveling at a velocity of 6.6 kilometers per second, or 6,600 meters per second. Plugging those values into the formula results in a kinetic energy value of 12.4 gigajoules, or roughly equivalent to 3 tons of TNT. But why is this small shift in orbit important? If you can detect an asteroid early enough, a tiny deflection is all that's needed to prevent a catastrophic collision with Earth. Asteroids travel immense distances over time, so even a small change in speed or direction can add up to a significant shift in their eventual trajectory. In fact, this method could be especially useful for asteroids that are discovered years or even decades before a potential impact, giving us time to intervene. The DART mission was a proof of concept, demonstrating that with enough preparation and the right technology, we could deflect an asteroid away from a potential collision course with Earth. Kinetic impact won't necessarily be the only method we use, but it's now a key tool in our planetary defense strategy. However, not all asteroids are the same. Some are solid rock, while others, like rubble piles, are loose collections of debris held together by gravity. The effectiveness of kinetic impact might vary depending on the asteroid's composition, which is something future missions will need to account for. That's where missions like ESA's Hera, which we'll discuss next, come into play. Now that brings us to the next chapter of this story, ESA's Hera mission, which launched earlier this week at the time of this recording on October 7th, 2024, aboard a SpaceX Falcon 9 rocket, while NASA's DART mission showed us that we can successfully alter an asteroid's orbit. Hera is about to tell us much more about how that happened. Hera is the investigator, the detective that follows up on DART's historic planetary defense experiment. Its primary objective is to return to the Didymos system and conduct a comprehensive survey of Dimorphos, the smaller of the two asteroids. DART's impact in 2022 altered Dimorphos's orbit around Didymos, but we still have so much to learn about the specifics of that collision. Hera will provide the first ever post-impact analysis of a deflected asteroid, unlocking new insights that could shape the future of asteroid deflection strategies. The spacecraft is set to arrive at Dimorphos in 2026 and will spend several months closely studying both the asteroid itself and the surrounding environment. Hera's detailed observations will focus on several key areas. First, the mission will map the crater left behind by DART's impact, revealing its size, depth, and structure. This will help scientists better understand the energy transfer involved in the collision. Hera will also measure the asteroid's mass and its precise shape, critical for assessing how much of Dimorphos was affected by the impact. But that's just the beginning. Hera will also delve into the internal structure of Dimorphos, something that could not be determined from Earth or the DART spacecraft. Understanding whether the asteroid is a solid rock, a loose collection of rubble, or something in between is crucial for determining how other types of asteroids might react to future deflection missions. What's even more impressive is that Hera isn't working alone. The spacecraft is carrying two CubeSats, small but mighty companions that will conduct their own mini-missions. These CubeSats, named Milani and Juventus, bring advanced technology to explore Dimorphos even further. Milani will perform a detailed surface mapping of the asteroid, capturing high-resolution imagery to provide a close-up view of the impact site and the surrounding terrain. This data will be invaluable for understanding how the surface was affected by the collision and for identifying any changes over time. Juventus, on the other hand, will use radar to penetrate beneath Dimorphos's surface, offering a groundbreaking look at the asteroid's internal composition. This marks the first time radar has been used on such a small celestial body, and it could reveal whether Dimorphos has a solid core or if it's more of a loose aggregate of rock and dust. Understanding this internal structure is essential, as it influences how asteroids absorb impacts and how their orbits might change in response. Hera will also study the broader effects of the DART impact, including any debris or ejecta still orbiting the asteroid. This will help determine how much material was thrown into space during the collision and how that may have influenced the deflection itself. By combining all of these measurements, Hera will paint a complete picture of the impact's effectiveness and provide data to refine future asteroid deflection techniques. Scientists will use this information to model different types of asteroid collisions and figure out whether similar missions could work on other, potentially more dangerous asteroids with different compositions, shapes, or sizes. Essentially, Hera's mission is not only to assess the success of DART, but to prepare humanity for the next time we might need to defend our planet from a space rock. It's incredible to think that humanity has progressed to a point where we may have a means of safeguarding our planet from the extinction-level threat of asteroids. While we hope we never have to use this technology in an emergency, it's comforting to know that we're making progress. The DART and Hera missions are just the beginning of what could become one of the most important scientific efforts of our time. Thanks for watching. If you enjoyed this video, feel free to give it a like. More videos will be coming soon. Next up will be a video about NASA's Europa Clipper mission, and I have plans for some more long-form content including a history of rocket engineering, the search for exoplanets, and the Big Bang. So subscribe if you'd like to see those videos as soon as they come out, and let me know in the comments, what do you think about the idea of deflecting asteroids? Does it make you feel safer? Let's talk about it. Once again, thank you for watching and clear skies to you all.